Hello. Today's video will be about the calculus power rule. We will, I'll assume that you can probably do some elementary calculations with it. This will be about the proof. So let's get started. So power rule here. And what it basically says that for some real number not zero, the derivative with respect to x of x to the r is rx to the r minus 1. Now, that's a very, very commonly used rule at all levels of calculus. Now, what we'd like to do is I'd like to discuss the proof. And the proof will be done in several stages. The first part of the proof is that we'll prove it for positive integers. It's the most common version. The second part is that we'll do the proof for negative integers, and so on. And this will require the reciprocal rule. And I can never spell reciprocal. So it requires the following rule here. It says that the derivative of 1 over g, where g is not 0 and g is differentiable, is going to be minus g prime divided by g squared. So I might sketch out a quick proof of that so we can do this. Third is we'll do the proof for r a rational number. That is, r is p over q, p not 0, p, q integers. And we'll do that right here. Maybe a little bit out of order. I should probably do this first and then go to here. That way we can pick up the negatives. But once we do this and do the reciprocal rule, the rest follows. But yeah, I might jump from 1 to 3. Then what I won't do for r real but irrational, you really need exponentials and logs. And if you think about it, if you want to talk about what x to the pi really means, you're either going to have to do some sort of limiting process or you're going to have to define it in terms of exponentials and logs, because the rest of these are maybe more natural. This one here, that's something else. So let's go ahead and get started. And I'll probably spend most of the time where proving this for x to the k, where k is a positive integer. Now, there's really, I know of two fairly quick ways of doing this. I'm probably going to emphasize the binomial theorem version more, but let's do two methods of proving for k with this restriction. So the two methods. And the first method is math induction. Now, of course, I have a video about mathematical induction and why it works and all this other stuff. A lot of people get that in their pre-calculus course. But basically what it means is that you show true for k equals 1. Two, assume true for k less than or equal to some n, for some n. And then show true 1 plus 2 implies true for n plus 1. And that basically means that there's no value for which the rule will fail. So 1 says it works for the first one. 2 says assume it works up to some n, and then we'll show that if it works up to some n, it has to work for all n. So let's start. So the first case with this math induction, I'm getting my little indices screwed up a little bit. Hopefully you can deal with that. So let's do 1. Let's go ahead and try this. Let's try k equals 1. Well, if you want to figure out the derivative of x, well, I assume most of you have already seen this, but in case you haven't, you take a limit as the change in x goes to 0 of x plus change in x minus x over change in x. And then we see that the x's cancel, and that's easily seen to be 1 because the delta x's cancel as well. So it's true for k equals 1, and we've done that. 2, assume true for k and 1, 2, all the way up to n. So third, so now let's do that. So now if I want to do the derivative of x to the n plus 1, we can now use the product rule. X to the n plus 1 is just x times x to the n. And the reason you write it that way is that we can use the formula for x to the n, but we can't use it for x to the n plus 1. And by the product rule, you know what that is if you're watching this. It works as follows. Now the very first one, we've already shown the derivative of x is 1. So that's x to the n. This, by the induction hypothesis, will be n x to the n minus 1. And then this multiplies through nicely. So this is n x to the n. And then a little bit of algebra, factor out the x to the n, because it's here and here. You get 1 plus n, and we get the formula we want. And so the math induction method goes pretty quickly. However, the second method, and I like it better for the following reason, we use the method of the binomial theorem. What the binomial theorem says is that if you take x plus y and raise it to the positive integer power, you get this. And now these things I'm writing down are called the binomial coefficients. The typical thing is n choose k, x to the n minus k, y to the k. And then the next to last one is n choose n minus 1, x, y to the n minus 1, and then the very last term is going to be y to the n. Now, I should tell you what all these things are. This n choose k is going to be n factorial, k factorial, n minus k factorial. Now, I do have a little video about these things. These things are called the binomial coefficients. And in your calculators, will sometimes have it C and R, or maybe like that. Those are other things. And basically what this represents is if you have n objects and you want to select k of them, let's say you have a class of 20 students and you want a committee of 3, the number of ways you can choose that committee is 20. Choose 3 would be 20 factorial divided by 3 factorial times 17 factorial. So that's what that is. And I can go on and on. You talk about Pascal's triangle and that sort of thing. I may as well do that. Pascal's triangle, this would be the n equals 0 level. The n equal 1 coefficients, you know what those are, because that's x plus y to the 1. Well, that's easy. The square, the quadratic, well, if you add these two, those give you the binomial coefficients for n equal 2. For 3, you add these two, and you get like that. And you can keep going as long as you want. That's 3, and that's 4. And it's a nice little handy way. And I haven't proved that, but you can prove that these numbers here are exactly these. And but it would take us a little far afield from what we want to do. It's a wonderful little theorem for combinatorial math. Now, how does that work? Well, the important thing is to notice what these coefficients are here. So it's important to know that n choose 1 is n. And that makes sense, right? Because if you have n students, you want to pick one, how many ways can you do that? Well, it makes a lot of sense. So now when I want to figure out what the derivative of x to the n is, I take this limit as a change in x goes to 0 of x plus change in x to the n minus x to the n over delta x. Then we let delta x go to 0. Now, this is where the binomial theorem comes in. This is the important stuff. We start off with the x to the n. And I think what I'll do is I'll redo this. I will box this in red, like so. We'll worry about this for a second. This thing in red here, this will be x to the n plus, remember, n choose 1, x to the n minus 1 delta x plus n choose 2, if we go as far as 2, x to the n minus 2 delta x squared. And this continues all the way down to n choose minus 1. That's another n. And then we still have to subtract the x to the n. And we're so close. We're a lot closer than it may look. Because now that we have all this stuff with the binomial theorem, what happens to these two? Clearly, they cancel. They subtract off. Now remember, this is equal to n. So now I have an n, x to the n minus 1 delta x. I'll keep this thing here. And then what I'll do is I'll put this in purple just to change things up. This will be n choose 2, x to the n minus 2 delta x squared. And it goes all the way out to delta x to the n. Right? Now, we still have this delta x in the denominator. Now, what we want to do is multiplicative. Let's factor out a delta x. Let's do it that way first, so it becomes clear. So let's factor out these delta x's that appear everywhere. I have an n x to the n minus 1. That's looking promising, isn't it? And what's left? N choose 2, x n minus 2, delta x to the first power, all the way out to delta x to the n minus 1 power, because I've factored one power of delta x from all of these. And the denominator still has delta x, doesn't it? So multiplicatively now, we can now cancel those. We no longer have a delta x in the denominator. And by the theorem that says that if two functions are equal, except for one point, then the limit as we approach that point is going to be whatever this limit is. A delta x equals 0 is now in the domain, so we can substitute. There is a delta x factor in every one of these. There's none here. So when we plug in delta x equals 0, this whole part's stuff is 0, and we get n x to the n minus 1 as we need. So you see, it's a binomial theorem in disguise. That is the proof for our this part right here. Okay. Now I think just to make it logically tight, let's look at positive. Let's look at a positive rational number. So now, suppose let's say p be a positive integer, and let's look at the derivative of x to the 1 over p. Now we're going to have to use a chain rule here. And the way the chain rule works is, let's start off with x to the 1 over p equals y. Now let's raise both sides to the p power. This is now x is equal y to the p. Now if I differentiate both sides, by the chain rule, well, by the regular differentiation, that side is 1. By the chain rule, this is going to be p y to the p minus 1. That's y is the outer function, times the derivative of y. Now, I don't know if you've had the chain rule or not, but if you have the chain rule, you have this result here. Now let's solve for dy dx. Well, you divide by p, and then you end up with dy dx. So you divide both sides by p. This is y. It's now the negative of this. But remember what y is. And remember, powers multiply when they do like that. So it's x 1 over p minus 1, and lo and behold, that's what we wanted to show. So this is basically your pth root function derivative. Now there is another way of doing that. You can use it. Well, this is kind of the inverse function argument. Now we're going to have to use chain rule again, because now if we want to talk about dy dx, where y is now x to the p over q, where p and q are positive rationals, well, this is y is equal to x to the 1 over q to the p. So now dy dx by the chain rule, remember that's an integer, multiplied by the derivative of the inside. Well, we already said what the derivative of the inside is. Okay, so that's the chain rule. So now let's do this. P times 1 over q. Now I have the following. X, I'm multiplying, so it's p over q minus 1 over q multiplied by x to the 1 over q minus 1. But remember, the powers add now. So the powers of p over q minus 1 over q plus 1 over q minus 1. And lo and behold, that's what we need. Okay? So next. Now suppose y is now x to the minus r, where r is rational and positive. And this is I'm trying to think of how to proceed here. Well, remember y is 1 over x to the r. And I'd like to, and what I'm going to do is I'll go ahead and use the reciprocal rule rather than do it for this specific thing. So the reciprocal rule, let's say g is not 0, g prime exists, and you wish to differentiate 1 over g. Well, that's going to be a limit as a change in x goes to 0. 1 over g of x plus change in x minus 1 over g of x, all divided by change in x. Now, we see right here, algebraically, we have different denominators, so we want a common denominator. So the way you do that is multiply top and bottom by g of x. Here you multiply top and bottom by g of x plus delta x. And that's all over delta x. Now the top, let's just do this. We have a g of x minus g of x plus delta x all over g of x plus delta x, g of x, all over delta x. And then you've learned in algebra that if you have a fraction over another denominator, you've probably learned that some time ago. So I'll do this. Now notice this thing here, g of x minus that. I want to factor out a negative sign, and you'll see why in a second. And I want to slide this here, and I'm going to treat this as two fractions. And I think I did the classical hurried student thing, forgot to write my limits. I know you, professor will probably take off points because technically speaking, they're not the same. They're not the same unless you take a limit because they have different domains. But now that we know that the limit of the product is a product of the limits, we know what this is. And this thing here, remember, g of x is continuous because it's differentiable. So this is now the negative of the derivative. In the bottom, this goes to g because g is continuous, and there's a second g, so it's g squared, as we expected. So finally, to calculate x to a negative power, if we wish, so now using that, I take 1 over x to the r, which is x to the minus r. And let's say we want to differentiate it. That's going to be the derivative, negative the derivative, divided by x to the r squared. Well, we know what that is, minus r, x to the r minus 1. The bottom is x to the 2r. So it's minus r, x to the r minus 1, times x to the minus 2r. Well, r minus 2r is minus r. And lo and behold, that's the formula we needed to prove. So let's save this one here. Power rule. All right. Now, finally, notice what we've done. Well, we've almost exhausted that, so I'll get a new one. So now, what about x to the r, where r is irrational? For example, r is root 2, r is pi, r is e, etc. Now, the thing is, and here's the problem. The issue is that in order to even define what x to the r really is, the classical definition is to develop exponentials and to develop the log function first. And then you'd actually, x to the r, you would write as x is equal to e to the natural log of x to the r, and you might not know what that is. Or you might know that from pre-calculus. So that's a case. And then you have to use the following facts. The derivative of e to the x is e to the x. The derivative of log of x is 1 over x. So then the derivative of x to the r is the derivative of e to the r log x, because those are equal. And that's going to be e to the r log x times the derivative of this. But we already know that this is e to the r log x times r. We already know that's 1 over x. But the very first thing, e to the r log x, that's just x to the r. And notice we have a power of x in the denominator, so this will be r x to the r minus 1. Now, notice that, okay, let's just save this of power 2. Notice that this thing here, the astute student could say, well, wait a second, if you're going to define powers like this, why couldn't you just let r be any real number, including rational, and you could have done it in one fell swoop? Well, that meant that you had to develop e, you had to develop its derivative, you had to develop the log function, and you can do that with integrals. And you can have to develop the derivative of that. And that usually comes well after the power rule. So if I want to be intellectually honest, I'd have to say that we really did the power rule for rational powers. We didn't, the extending it to the irrational powers required more math than many of you have when you first seeing this. But that's actually how it goes. So thanks for watching.